This video is brought to you by mywayteaching.com.
In this part, let us study effect of dielectric on capacitance. Okay. Let us see how capacitance of a parallel plate capacitor is modified when a dielectric is present. Okay. The dielectric constant of a substance is the factor by which capacitance increases from its vacuum value when the dielectric is inserted fully between the plates of a capacitor. Okay. See, we have two charged plates, two large plates, each of area A, separated by a distance D in case of parallel plate capacitor. And the charge density on the plates is given by plus or minus Q, corresponding to the charge density plus or minus sigma. When there is vacuum between the plates, E naught is equal to sigma by epsilon naught, isn't it? So the potential difference is given by epsilon naught into D, and the capacitance C naught is given by Q by V naught is equal to epsilon naught A by D. Okay. Consider next a dielectric which is inserted between the plates. Till now vacuum. Now we are inserting dielectric, fully occupying the intervening region. The dielectric is polarized by the field, and the effect is equivalent to two charged sheets with surface charge density sigma p and minus sigma p. So the electric field in the dielectric then corresponds to the case when the net surface charge density on the plate is given by plus or minus sigma p. So that is given by E is equal to sigma minus, when we have inserted dielectric already here. Okay. So now the potential difference across plates is given by E into D, which is equal to sigma minus sigma p by epsilon naught into D. Okay. For linear dielectrics, we expect sigma p to be proportional to E naught, that is to sigma. So sigma minus sigma p proportional to sigma. So we can write sigma minus sigma p is equal to sigma by k. So where k is a constant characteristic of the dielectric, and here k is greater than 1. So now we can write V is equal to sigma d by epsilon naught into k. And if you substitute sigma q d a epsilon naught into k. Okay. But we know capacitance is given by Q by V, isn't it? So if you substitute V here, we get capacitance as epsilon naught Ka by D, and the product epsilon naught K, this product we call it as permittivity of the medium. Okay, and it is denoted by epsilon, which is equal to epsilon into K. Okay, for vacuum K is equal to 1. So in that case, only for vacuum epsilon is equal to epsilon naught. Okay, and this is called as permittivity of the vacuum. And the dimensionless ratio K is equal to epsilon by epsilon naught. And it is called dielectric constant of the substance. Okay. And it is clear that K is greater than 1. So, the dielectric constant of a substance is a factor by which the capacitance increases from its vacuum value when the dielectric is inserted fully between the plates of a capacitor. Though we arrived at equation for the case of parallel plate capacitor, it holds good for any type of capacitor if you take. Okay, it is a general one. Electric displacement. See, we know the notion of dielectric constant and we derive the equation that is K is equal to C by C naught without giving the explicit relation between the induced charge density and the polarization P. See, without proof, let us consider the derivation, that is induced charge density is equal to P dot n cap, where n cap is a unit vector along the outward normal to the surface, and this equation is true for any shape of the dielectric. Okay, for the slab, P is along n cap at the right surface and opposite to n cap at the left surface. Thus, at the right surface, if you consider the figure, at the right surface, induced charge density is positive. At the left surface, induced charge density is negative. So, putting the equation for electric field in vector form, we get E dot n cap is equal to sigma minus P dot n cap by epsilon naught. Or in other words, we can write epsilon naught E plus P dot n cap is equal to sigma, and the quantity epsilon naught E plus P is called electric displacement, and we denote this by D. Okay, this is electric displacement. Okay, so the significance of this electric displacement, and this electric displacement is a vector quantity, first thing, and we can write this electric displacement as D is equal to epsilon naught E plus P dot in vacuum. E is related to the free charge density sigma. When a dielectric medium is present, the corresponding role is taken by D. So for a dielectric medium, it is this electric displacement, not E, that is directly related to free charge density. Since P is in the same direction as E, all three vectors, that is P, E and D, are parallel. And the ratio of magnitudes of D and E, if you take the ratio of magnitudes, D by E is equal to sigma epsilon naught by sigma minus sigma P, which is equal to epsilon naught into K. Thus, D is equal to epsilon naught K into E, and P is equal to D minus epsilon naught E, epsilon naught K minus 1 into E. So this gives for electric susceptibility, which is defined before. So that is, electric susceptibility is equal to epsilon naught K minus 1. Okay. Now let us see a simple example. A slab of material of dielectric constant K has the same area as the plates of a parallel plate capacitor, but it has a thickness 3 by 4D, where D is the separation of the plates. How is the capacitance changed when the slab is inserted between the plates? Okay. Let E naught is equal to V naught by D be the electric field between the plates when there is no dielectric and the potential difference is V naught. And if the dielectric is now inserted, then again the electric field will be E is equal to E naught by K. Now we are inserting the dielectric, and the potential difference will be V is equal to E naught 1 by 4 into D plus E naught 3 by 4 into D by K. So here we can take E naught into D common. So we get 1 by 4, 3 by 4K, which is equal to V naught K plus 3 by 4K. So the potential difference decreases by the factor K plus 3 by 4K. While the free charge Q naught, so here that potential difference, it decreases by the factor which is given by K plus 3 by 4K. Isn't it? Yes. While the free charge Q naught on the plates remain uncharged, so the capacitance, thus the capacitance increases. So the value of capacitance we know already. C is equal to Q naught by V, and we have already calculated the expression for V, which is equal to V naught into K plus 3 by 4K, isn't it? That gives 4K K plus 3 Q naught by V naught. and this Q naught by V naught, we know that it can be represented by C naught, because C naught is equal to Q naught by V naught, isn't it? So the final value of capacitance is 4K by K plus 3 into C naught. So here the capacitance increases, and first we got the value of V and now we got the value of C. Okay. So before inserting the dielectric, potential, the value will be different, and after it will be different.